Hello everyone. In this video, I'm going to demonstrate our y86 64 sequential processor. But now we have only fetch and PC update stages, as you can see on my window. Okay, so let's get started. So I put everything, the figures we have seen in the previous the tutorial into fetch unit. So, but you can see all the outputs are given, like I code, iPhone, RA, RB, VLC, and VLP on the left-hand side. And for PC update states, because we don't have all the valid inputs to this stage, but we have only P value available. So we just have a direct connection between P and PC update, okay, over here. Okay, but the timing when we actually propagate this P to next PC uh, will be um, will be different, and we need a time. We have our own timing diagram, and I have my own timing diagram when to start this PC update stage. So it will be, so new PC will be output at a certain cycle. So we'll see that soon. And here we have enough space between fetch and PC stage because we don't have other stages yet, but we will include them in this design file. And on the down below, you can see two counters. And first counter shows the number of cycles we executed, we used for current instruction. The second counter shows the total cycles we used for this whole program. And then here we have one probe that shows total number of instructions we have executed so far. Okay, so we use this information to see the exact timing, what we are actually execute and how much instructions. So for example. And then in terms of program we are going to run, so we will use a common program we all know about is the ASUM, the array sum program. And I just see object file of this array sum YO file for our reference. And I already converted this to memory file and then loaded into instruction memory inside fetch unit. Okay, let's run this simulation after we reset. Okay, before we go to there, we start execution. So here we have an important assumption, which is the address of the first instruction, because the later instructions we can calculate, but the first instruction we should have assumption like that the first instruction will be stored in the memory address 0000, all zeros. So as you can see in the probe for what's that? The current PC instruction, the new PC here. Okay, so when we start this program, then it starts fetching at memory address 0. Okay. Okay, and then I'm going to tick 10 cycles 10 times because it takes 10 cycles to fetch whole instruction, 10 bytes instruction, right? And then we will see whether we fetched and then outputs correct values for here. We can see these probe values over here. Okay, and then while I'm ticking, you can watch down below. So how many times I tick. So let's get started. So I tick 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So we just ticked 10 times, and this counter shows 10 in decimal. It doesn't mean we finished cycle 10. It means we just finished cycle 9, and then we are ready to start take cycle 10. Okay. So then we got the output on the Logisim file, and then let's compare this output with actual machine code in the memory file. So first, after we read first byte, we have iCode and iPhone. So iCode and iPhones are 1, 1, and 0, or 3 and 0 in decimal. So we got, then in the first byte in this machine code, we have 3 and 0. Okay, it is correct. And then in the second byte, we read RA and RB, which is all 0 and all 4. All 0 and all 4. Sorry, so RA and RB are 1, 1, 1, 1, F and 0, 1, 0, 0. Okay. Yeah, then it is correct. F and 4. And then for the later 8 bytes, they will be stored in value C, because this IR move instruction has a register field. Okay, maybe you remember what I mentioned in the tutorial session. So we should have a align module to read the VLC correctly, and also RARB. So anyway, for the since it is IR move queue instruction, we read bytes from 2 to 9. Then we got 2 to 9 is from here to end. Okay. So then we got 200 in hexa value in the Logisim, but in the assembly object file, we have 0002 and many zeros. This is not 0, just 200 in hex. Is it correct or is it wrong? Actually, this is correct because we are using little endian in y86. Then we need to reverse. We store higher address in lower place in the register. So we read first bit, which is okay. Actually, this is we read first address, the current address, and then put it into the least significant bit, and then put next byte into the next significant least significant bit, and so forth. So that's why we have 200 in the what's that, in the Logisim probe over here. Okay, so if you are not familiar with endianness, like big endian or little endian, maybe you can Google it about it. Okay, and then okay, we actually correctly fetched a whole instruction or whole machine code, and then next part is about the next address of the next instruction in PC, so in val-p. Okay, so we got val-p with A in hexa, and then let's see the next address of the next instruction, which is A in hexa. Okay, it is correct. But the PC register is not updated yet because we just finished first 10 cycles. But based on my timing diagram, it takes 20 cycles in decimal or 14 cycles in hexa So we need more cycles to finish this entire instruction execution. So then at cycle 20, this the PC update stage will output the value of val p, because we just hard coded with these two values. But you will start outputting, reading this val p and then outputting the val p to a new PC at cycle 20. Okay. Anyway, we are at cycle 10. So let's run 10 more cycles. And then let's start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So we finished next 10 cycles, and then we are about to start next instruction because we see 0 in the counter. Okay. As you can see in this new PC probe, we see the updated PC value with A. Okay, it's good. And then we are about to fetch the next instruction, and then let's take 10 more times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then let's take a look at the outputs of fetch unit. iPod, iPhones are 4 and 0. Oh, sorry, 8 and 0. Okay, then we got 8 and 0 in the machine code. It's correct. And then for RA and RB, we got F and F. But in the second byte, we don't have F and F. We have 3 and 8. Why it is different? Because we are fetching call instruction, which does not have register field of register field. So then it will be aligned by align module. So then so it will align module just outputs 2 Fs for RA and RB, and then it will output the value the bytes from 1 from here 1 to 8 from in the machine code to the VLC. So when we read these bytes from 38, then you see this correct value in the VLC. Okay, so we see 38 in VLC, and we see 38 in this machine code. Okay, this is correct. Good. And then what about next instruction? So next instruction should be 1.3 in this machine code object file. Okay, we have a 1.3 in the VLP as well. Okay, cool. Okay, so then we fetched correct instruction and we updated VLP as expected. So then let's take next 10 cycles to see the updated PC. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, then we can see updated value with what's that? 8, 30. Sorry, 38. Okay. Okay, then let's then after we run all these instructions, then we can see whether we fetch all this machine code correctly or not. Okay, so you can test whole this fetching process with your design. Okay, this is it for the fetch stage demonstration. So in the next video, I'll talk about decode and write back stage. Thank you.